Hey everyone, it's about 7 o'clock here in Troy, so we're going to kick things off for our first talk of the semester. We should all be back from break now, for better or for worse, and so we're going to be picking our meetings back up again. Usually in the fall, we try to focus on a lot of beginner-friendly topics, and we try to get everyone kind of up to speed on the fundamentals of cybersecurity. And then in the spring, we try to dive in a little bit deeper. And so to kind of kick that deeper trend off a little bit, I wanted to talk about control flow integrity, which is a really amazing set of mitigations. It's a family of mitigations, I guess I should say, that help address a lot of the issues that we discussed last semester, specifically with ROP and the more advanced binary exploitation talks that we were diving into. So without further ado, let's dive in there. Because this is a bit more of an advanced topic, I do want to give a little bit more of a background, especially because I don't know how many people may be joining for the first time this semester, and I want to make sure that we kind of are able to address some of the underlying concepts and provide resources so that if people don't fully understand what's going on when we're throwing around a lot of this technical terminology, people are able to go back and look at our previous videos, or people at least know they have a sense of what we're talking about, and they have a sense of the bigger picture. So specifically, CFI is a mitigation for a technique that we talked about last semester called ROP. And so we're going to cover that a little bit, and then we're also going to talk about the two different types of CFI. So there's forward edge CFI and backwards edge CFI, and kind of taken together, they make this incredibly secure system. And then the other thing that we're going to talk about is a couple of different types of implementations of both those forwards and those backwards edge CFIs. So some of you may have heard of pointer authentication codes before, or PAC. Those are really, really famous. Those are probably one of the better known implementations, just because recent iPhones actually have hardware support for that now, which is really cool, and definitely adds in a welcome layer of security to them. And then we'll also be talking about control flow guard, which is often abbreviated to CFG, which is kind of confusing because that can mean a lot of different things. But for the context of this talk, when we say CFG, we'll be talking about control flow guard. And control flow guard is a really cool mitigation that was kind of Microsoft's implementation of a form of forward edge CFI. And then we'll also be looking into shadow stacks, and specifically a collaboration between Microsoft and Intel that they are just now starting to build support into. So let's kick things off and let's dive into that background a little bit. Just a quick history here. This is definitely not intended to be a comprehensive history of computer security in any way at all. But the main idea I wanted to convey here is in 1996 there was a really seminal paper. There was a really famous paper about basic buffer overflows, and they talked about overwriting return addresses and hijacking control flow by just overwriting a return address. So when your function returns, it will return to a piece of code that you can control. And then the next year in 1997, we saw a demonstration of a technique called ret2libc, where you're returning to functions in libc, in the C standard library. And so that gives you a lot of freedom to do things like return to the system function, where you can just give yourself a shell through that. And kind of as a result of this flurry of security research, we saw some of the earliest mitigations being introduced. So one of the really early ones was stack guard, which was effectively a form of a stack cookie, which just protects that return address a little bit so that it makes it a little bit harder to pull off those techniques. And I couldn't figure out exactly when shellcoding was introduced. Shellcoding is just a basic form of injecting malicious code into a running process, into a binary. But I believe that it was somewhere within this time frame, somewhere within that area. But we see this trend continue as more and more techniques are developed, more techniques both for exploiting systems and also for mitigating those exploits. And we have this cat and mouse game. So as shellcoding is introduced and as attackers are able to inject their own malicious code into processes and they're able to run whatever they want, we see in 2004 FreeBSD and Linux start to add support for this thing called an NX bit, or a no execute bit, which will mark a section of memory as non-executable. And so that's a form of a mitigation that will allow you to make it so that even if attackers can inject code into your process, they can't run it, they can't execute it. If you can write to process memory, you can't then execute that same process memory. And so that kind of killed out this technique of shellcoding, but attackers very, very quickly learned to adapt, and they learned to work their way around, and they learned to find new techniques. And return-oriented programming, or ROP, was one of the new ways that they were able to continue to inject their own code and execute malicious code in spite of this mitigation. And interestingly, right around that same time, right after that NX bit is added, and that shellcoding technique is kind of killed off for the most part, Microsoft starts researching CFI. They start researching control flow integrity. So Microsoft was clearly thinking ahead here, and they were clearly laying down the groundwork for this this way to bypass, to eliminate a lot of these techniques like ROP or JOP or other return or call or jump oriented programming techniques to jump around. And then in 2014, Microsoft actually enabled Control Flow Guard in their proprietary Visual Studio compiler. And so we can see it took about 9 years between when they started researching CFI, or at least between when the earliest like publications that I could find online from Microsoft referencing CFI came out, and when it was actually production ready. So that should give you some idea of the complexity that we're dealing with here. But I think this is a really interesting way to look at control flow integrity as this game of cat and mouse, because we can see there was this era where shellcoding was the go-to method when you wanted to inject your own malicious code. And then a mitigation was introduced, and a new technique of return-oriented programming popped up, and suddenly that was the go-to way that everyone was using to inject their own malicious code. And now we're seeing Microsoft enabling more and more control flow integrity mitigations to try to stop return-oriented programming and that technique. And so I think it's going to be a really interesting couple of years as we see attackers try to find ways to break this implementation and try to find ways to get around it and continue to find new and creative techniques to do malicious actions. So we've been talking a lot about return-oriented programming, but for those of you that weren't able to make it last semester, or for those of you that maybe just be joining for the first time today, I wanted to give like a super duper basic primer here of what return-oriented programming is. And if you are curious and you want to learn more, feel free to go back to our previous videos and feel free to watch those to learn more about it. But basically what return-oriented programming is it's a technique where you can take these little gadgets that are just like a couple of instructions at a time, usually ending in a return instruction, and you just chain these all together. And the really clever thing about this is you're not rewriting code, you're not writing new code, you're reusing code that already exists in the benign process, in the original process that's running. So you're not writing to memory, so that non-execute bit suddenly is no longer an issue. So just a quick little visual aid here. If this is our stack and we've just made a bunch of A's. We've just written a bunch of A's to it to smash whatever we have on the stack until we get to where a return address would live. We can suddenly put a return address of some code in libc or some code in our binary itself, and we can return to that. We can execute an instruction, and then at the end of that gadget, there's going to be another return instruction. What that instruction is going to do, if you remember, is it's going to look at the next thing on the stack, it's going to pop that off, and it's going to start executing there. So it's going to return from this gadget directly into this gadget, and then directly into this gadget. And so we can chain all of these little tiny, like 1 to 2 instruction gadgets together to execute whatever series of instructions we want. And that demonstrates a really important topic, and one that we'll be talking a lot today, which is control flow. And basically what control flow is it's the order in which you execute your code. So if you have some if statement where you can take one branch or you can take another branch, the control flow is going to be the flow, like your flow through that program, like whether you take that true branch or that false branch. Or like if you have a for loop, it could capture like how many times you go through that for loop and things like that. So just another visual aid here. I've written just a toy C program here. So if we're stepping through this one instruction at a time, we get to this call instruction, and when we get to that call, we're going to be jumping into this other function. So we'll be writing our address to the top of the stack, or to the stack, and then we'll be jumping in and executing this function here. And after we get to the end of this function, when we return, we're going to look at what's on the top of the stack, and we're going to pop that that address off, and we're going to just resume executing right where we left off. And so the two things that we really want to be thinking about here from a security perspective are when we make that call and when we return, because in both of those cases, we're just telling the computer, hey, here's an address. Hey, just start executing here. And so those are really common targets for an attacker, because you can overwrite a return address on the stack, and you can also overwrite, if you have a variable that's a function pointer, you can often overwrite those as well. And so those are things that we really want to be thinking a lot when we're trying to maintain the integrity of this control flow. So control flow integrity, as I was talking about before, is just a type of mitigation where you're going to try to stop an attacker. So you're going to try to stop a hacker from hijacking that execution, hijacking the flow of execution throughout a program, usually by stopping them from overwriting return addresses and or stopping them from overwriting function pointers, because those are two really, really common targets for attackers. So forward edge CFI, which we talked a little bit about before, is basically just protecting function pointers. So when you have a function and you call that function, you want to be thinking about like how you're jumping forward and what address you're jumping to. So control flow integrity, forward CFI, is just going to be making sure that when you call a function pointer, the target, so the address that you'll be jumping to and executing at, is actually valid, and that's not going to be malicious code there. And similarly, backwards edge CFI is just going to be protecting those return addresses. So when you try to return back to where you were executing before, it makes sure that that address is actually a valid one, and it's not going to be jumping into malicious code. So we've talked about what CFI is, and I want to spend the rest of the talk here just going over how it works and some of the common implementations. So the first one I'm going to talk about just a tiny little bit is going to be pointer authentication codes, but we're going to be focusing for the most part on Microsoft's implementations, because those are much easier to learn about. They're much better documented. The basic idea of pointer authentication is that we have these addresses, but a lot of these addresses are kind of just empty. They're kind of just a bunch of bits that we never really use or we never really get to. So in this case, we're looking at a 32-bit system, and so only 32 bits are actually used in the addresses out of 64 bits. But even on a 64-bit system, you're not usually using all 64 bits for your addresses. Usually you still have bits that are unused. And so the idea of pointer authentication is that we can take those unused bits and we can cram some more interesting metadata in there. So some of you may be familiar, especially if you saw our series of crypto talks last semester, of what message authentication is. But effectively, message authentication is just going to be a way that we can verify that the sender of a message is actually who they say they are. So this is used really commonly when you want to verify, if you get a if you're talking to an ATM, for example. If you're writing a piece of software to communicate with an ATM, you want to make sure that the ATM is in fact an ATM and not just a malicious actor impersonating an ATM, so that they can get your login information. They can get your PIN or something like that. But within the context of these pointer authentication codes, that authentication code is just going to be some way that the manufacturer can sign that. They can say, yes, I am Apple, and I sign off on this. I say that this is a valid address because I compiled this code. And so that makes it really hard, because if we overwrite an address, now all of a sudden we would have to authenticate the new address. And unless we have a secret key that in theory only Apple should have, then there's no way that we can do that. And so this is a really clever implementation, but the issue is that this does require hardware support, because we are fiddling with these addresses. We are fiddling with these pointers, and we're storing information in there that it was never intended to be stored. So that's a really, really quick rundown on pointer authentication code. I just wanted to give a very brief overview of it, because it's a technique that you will probably see out there, and it is one of the more common techniques to implement control flow integrity, just because it's used in iPhones, and iPhones are a very common target for security research. And I expect now that Apple is rolling their own silicon for their MacBooks, I expect that we'll start to see these roll over into the desktop world, which will be really interesting as well. But the next technique that I want to be talking about a little bit here is control flow guard, which is Microsoft's implementation of forward edge CFI. This is actually the most documented, as far as I could tell. Clang does support something really, really similar, where they have Clang CFI, and that's a very similar technique that will attempt to implement forward edge CFI. But interestingly enough, Clang CFI is not as well documented as control flow guard is, and also it's not as widely spread, I don't believe. For a long time, Google Chrome was using Clang CFI as a mitigation within their browser to make sure that they were more secure. However, at this point, control flow guard is actually much more widely used, because it's supported not only by any program that you compile for Windows, but also it's actually enabled in the Windows kernel. So as of Windows 10, it is if you're trying to exploit the kernel, you will actually have to be dealing with control flow guard, and you'll have to be bypassing it. However, when you're compiling a user space program, it's not enabled by default, and so you do actually have to pass, I believe it's /guard, as a flag to that compiler to enable it. basically a very high-level overview of how control flow guard works is when you compile a binary, you're going to scan through that and you're going to figure out every possible valid target for a call or a jump instruction. And then you're going to mark those off. You're going to take a little note of those and you're going to say, hey, this address is valid. All of the other addresses are invalid. So then at runtime, you're going to check that address in the bitmask every time you have a call instruction. So when you call, instead of just jumping directly to that address, you're going to look up in this bitmask that you created at compile time, and you're going to say, wait a minute, is this valid, or is this going to be malicious code? Is this a valid start of a function, or is this going to be some address on the stack that an attacker might control? So the way that we generate these bitmasks is actually pretty straightforward. It's pretty intuitive. Basically, we're going to take a list of all of these addresses, and then as we're compiling that program, every time we come across a jump instruction, or every time we come across a call instruction, or anything like that, we're just going to take a little note, and we're going to say, okay, this address, this one is valid, but this one is invalid. And so we're going to record those valid addresses, and we're going to mark those as a 1, and any invalid location is going to be a 0. And so then we're going to take all of that together, and we get this binary string of 1s and 0s, where we know index 0 here, or the highest index, is going to be 1 because that's a valid jump target. Whereas the second one is not. One interesting caveat about this is that we kind of have to be thinking about the granularity of this bitmask that we're making. Because if we have a, if we're trying to do this for every address, then we'll have to be looking at every, like 8th byte, essentially. We'll be having to look at every possible slot, every possible 8-byte aligned slot that we can. And if we're doing that, then all of a sudden this bitmask is going to take up 1/8 of our total memory. And if we're dealing with a very complex binary that takes up a lot of memory, like if you're using, like if you're writing Google Chrome, for example, because we talked about how Chrome used to use Clang CFI, and Chrome is notorious for using a lot of memory, suddenly this becomes a lot less appealing, because if you have maybe 4 gigabytes that's dedicated just to your browser, suddenly you're going to have to allocate an extra half of a gigabyte just for this bitmask. And that can have some serious performance ramifications. So we kind of have to strike a balance. We have to say, okay, we want to make sure that we have the granularity to keep things secure, but we also want to make sure that we're not using up an extra 1/8 of your memory every time we run a process here. And then if we're actually looking at real-world programs, one really easy way to tell if they're using control flow guard is if we see this instruction here. So this call guard check iCall. And then we can also see in the instructions before that, we're going to be taking in an address and we're going to be setting up for this call. So we're going to be passing in an address as an argument to this function. We verify that address, and then we call that address. And if that address is invalid, then this function is just going to panic. It's just going to kill the program. It's just going to crash. So if you've ever seen, like on your data structures homework, if you've ever seen that stack smashing detected warning and then your program crashes, it's going to be a very similar thing, because it's going to call this helper function to verify that cookie, that stack cookie. And if that cookie is invalid, then it's just going to terminate your program. It's going to print out that warning sign. Well, this is a really similar technique where it's just going to call this other function, but instead of verifying a cookie, it's verifying an address. And then if it's invalid, then it's just going to crash. It's just going to terminate your program. So that is forward edge CFI. However, the issue with forward edge CFI is this only works when you're calling an address. So for example, when you have a function pointer, this works great because you're able to look at that function pointer and you're going to say, okay, here's every valid place where it could be pointing. Here's every valid function that I want to be able to call, and I don't want to be able to call any other code. I don't want to be able to call any other functions. But when you're returning from a function, this isn't going to work as well because you're not calling it, and so it can't verify that code. And also, oftentimes you're returning to the middle of a function, so you can't whitelist at the function level in the same way. However, that shadow stack that we were talking about before is a great way to address this problem because that shadow stack is going to protect that, that return address, and it's going to give you a form of backwards edge CFI. So again, we'll be focusing on specifically Microsoft's implementation here, but Clang does actually also support shadow stacks. So if you're on Windows or if you're using Clang on another operating system, you can actually compile your programs with forward edge CFI through either control flow guard or Clang CFI, and with backwards edge CFI through the use of shadow stacks, which we'll be talking about here. But basically, the idea of a shadow stack is that when you set up a normal stack frame to execute a function, you have your local variables, and then you have some like function metadata here. And specifically what we're really interested in is this return address, because this return address is going to be on the stack right there above that, that stack frame. It's going to be at the base of that stack frame. And then these local variables are going to be within that stack frame. So as you start reading into these local variables, you're going to be flowing up into that return address, and you can actually overwrite that return address. And so then all of a sudden, instead of being this valid address to return to, this valid code, suddenly you can corrupt that and you can make that whatever you want. The idea of a shadow stack is basically that you can copy that sensitive stack metadata, like those return addresses, into another region of memory that should, in theory, be safe from these overflows. So now, when we set up that stack frame and we get ready to execute this function, we just take a copy of that return address and we stick that on the shadow stack. And then as we finish executing that function, we're just going to look at the shadow stack and we're going to look at that return address that's on the real stack, and we're going to say, okay, do these match up? And if they do match up, we know that everything is fine. But if they don't match up, we know that there's been some kind of shenanigans going on, and someone has corrupted our stack, so we just terminate the program. So when something goes wrong, as we can see before, or as we can see here, we've corrupted this stack frame. All of a sudden, that return address is just pointing to garbage. And when we try to verify it and we try to check that against what's on the shadow stack, we can see they don't match, and therefore the program has been tampered with, the process has been tampered with, and we can just terminate, we can just kill it. One really important consideration, though, that we need to think about is where we put this shadow stack. So I was reading about some very early implementations that would just say, yeah, we're going to put that shadow stack on the opposite end of the stack frame. And so this means that if you have an overflow and you're overflowing upwards, then yeah, you're not going to overflow into this shadow stack. But if you have some kind of controlled write, you can just overwrite this however you want, and this doesn't really do you any good. So in this case, it provides you a little bit of extra security, but if you have a controlled write, you can easily bypass this. Or even if you have this function call another function from within that child frame, sometimes you can corrupt a previous stack frame here. And you could actually corrupt this return address, or this address on the shadow stack. One much better implementation that we saw actually in Microsoft's original implementation of a shadow stack was the use of a guard page. And basically what that guard page is going to do is it's going to detect any kind of access whatsoever. So you can read to it or you can write to it, and that will trigger this guard page, and it will just terminate your program immediately. And we will sandwich our shadow stack in between these guard pages. So if an attacker is scanning through memory and looking for this shadow stack, they're going to hit one of these guard pages first, and they will have that program killed on them. So that's a really cool idea, and that's much more effective. The issue is that their implementation, Microsoft's implementation, actually had a race condition in this. So when you had a complex system with many threads running, you could actually skip this check of the shadow stack, and you could bypass the backwards edge CFI completely. And so Microsoft decided to kind of not ship that, not put that out into production, because they were able to find this bug first. Their internal red team was able to find this bug, and they kind of went back to the drawing board. And so what's actually being used in this CET, this newer implementation of a shadow stack, is they have built-in hardware support. And so instead of writing this shadow stack into regular process memory, they're actually writing in a special memory segment that not even the kernel can access. And the only way that you can touch this is by using a special set of instructions that will push and pop to this shadow stack. And so it's a really amazing tool. It means that it's incredibly difficult to corrupt that stack frame, because you can't access it with a normal read primitive. You can't access that shadow stack with a normal read primitive. You have to use one of these dedicated instructions. The issue, though, is that this requires hardware support, so you can't just run this on any system. I had actually planned a really cool demo for today where I could show this off, because I think it's a really amazing piece of technology. But because it requires that hardware support, turns out trying to run that in a VM doesn't work so well. So hopefully this becomes more mainstream. This hardware was actually only released a few months ago. I believe Intel collaborated with Microsoft to develop this hardware support for shadow stacks. And it was the first supported processors were Tiger Lake series, which were just released a few months ago in the fall, I believe in September or October. So it'll be quite a while before we see this become mainstream, I think. But I believe that's it for today. We've talked about 3 different implementations of control flow integrity, both forward edge CFI and backwards edge CFI. And we've talked about how hopefully we're going to see the state of computer security change pretty radically over the next couple of years as this becomes more mainstream. Because a lot of these techniques that we've learned, such as return-oriented programming, suddenly are no longer feasible, and attackers are going to have to be finding new and creative ways to bypass these mitigations. So that's it for me today. I hope you have a wonderful rest of your day.